Okay, let's see if we can get one more of these in before I need to pause. Okay, so we've talked so far about the past models up to Rutherford. We talked about the Bohr model. We talked about emission spectrum. We found that the Bohr model did a great job describing the behavior of hydrogen, but it fell apart at that point. We found that the scientists at the time realized that it was doing a great job to predict the behavior of hydrogen, but the reason that it could not describe the behavior beyond hydrogen was that we were still assuming that electron is a particle. Ooh, I know we all want to assume that, but that's actually, we've since decided that it is not. Okay, so let's take you into the next concept. And now this is again one of those that's going to blow your mind. So again, please do not expect to understand this. I'm going to describe it to you the best I can so that you can see the historical background. The only things I'm expecting you to get from this is to see that this has progressed over time and that we are going to then use the learnings from this model to predict behaviors later. Again, this is not what we do in chemistry. We come up with theories and we use those theories to do predictive things. So far, the quantum mechanical model continues to describe behaviors well enough that we can use them to do really cool and interesting things in chemistry. So whether or not you understand the theory doesn't matter. The key is learning the outcome of that model allows us to develop theory. The theory of that, the outcome of that theory is allowing us to predict behaviors that allows us to continue to use chemistry in a useful and functional way. Okay, as we jump into quantum mechanics, what is quantum mechanics? So just in a super simple form, classical physics is the macroscopic physics. It's what we're used to. You throw things, they fall and they drop. This is classic physics. It's the stuff we can see at a macroscopic level. However, this does not do a good job of describing things at the subatomic level. So there's a theory that has been developed called quantum mechanics that is attempting to describe the behavior of matter and energy at the atomic and subatomic level. And some of this is a little mind bending, but I'll give you do the best I can to summarize it briefly and then move past it so you don't have to spend a lot of time on it. We will not be testing you I will not be testing you on quantum mechanical theory. The questions in the quiz related to this is really the main concepts I want you to take away from this. So as long as you can understand those key concepts, then you should be fine. Okay, so let's talk about what quantum mechanics says about atoms and electrons. Okay, so there were a couple smart guys. There's a lot of these smart guys that are coming up with a couple of theories. These are all getting to be towards the beginning of the 1900s. So de Broglie came up with this idea of wave-particle duality. He says that light's a wave, but light can occasionally act as a particle, and there was a double-slit experiment that showed that it can behave as both a wave and a particle. He said he hypothesized that if a wave can act like a particle, then a particle, such as an electron, can act as a wave. I know, mind blowing, but let's just believe that this is true for now. Then there was this guy named Heisenberg who came up with the Heisenberg uncertainty principle, which you've probably heard of. This is the one that says because an electron has the nature of both a particle and a wave, it's impossible to know both its exact position and its exact speed at the same time. The process of measuring one impacts the other. So if you were to try to measure its position, you would impact its speed. If you were to try to measure its speed, it would impact its position, and therefore you cannot know exactly where this is at any given point in time. So with lots of complicated math that is way outside the scope of this class or probably anything taught at Las Positas, let's just say that these things are true for the purposes of theory. So what do you really need? What does this mean and why do you care? What this means is you cannot know the precise path of of the electron's orbit. You don't know where it is at any given point in time, and there's no way for us to predict its actual location. What we can do though is we can calculate a probability of where we think it might be, and we can develop these probability maps to indicate where we think it will probably be. Okay, so let's get to what that looks like. So those concepts, there was this quantum mechanical model was developed by Schrodinger and lots of other people. We've heard of him. He's the cat guy. And many of his colleagues developed a quantum mechanical model for the atom, which is the step up from Bohr's model. And what they've done is they've said, in addition, instead of these orbits that look like planets orbiting the sun, we have these things called orbitals, which is just a little bit more complicated. And of course, it's got so it at one level it operates very much like Bohr's model, where you have the energy levels n1, 2, 3, 4, 5. But within each individual level, you have a lot of weird and wonky stuff happening. That doesn't make sense from a classical physics perspective, but it does actually make predictive sense when you start using this information to predict behaviors, and it works for some reason. Okay, so an orbital is a region of space around the nucleus where there is a high probability of finding an electron. And these are based on some really complicated equations and very complex math that allows you to map out what the shape of this particular orbital would be. Now, it's not for you to understand the math, but what we will tell you is the results of their calculations and how we can use that in a way that is interesting and, again, predictive for us. This tells us the math in these wave equations and these other things that are tell us that we will not know exactly where the electron will be, but it will be somewhere. It will probably be somewhere within this orbital. These different orbitals have these spaces of probability, have different shapes based on where they are in the atom, okay? And we're gonna talk about what that looks like, and I'm going to be defining these for you, but this is the essence of what the quantum mechanical model is. How it changed from Bohr's model is we've now gone from these orbits, which is these circular orbits around, to these orbits now within those orbits have sublevels that have these weird and wonky shapes that have been predicted. So you still have the orbit, which is the primary level, but within those orbits, you have all this other weird stuff happening that can be predicted by these complicated equations. Okay, so just to get the concept of what a probability map would be, as in the probability of finding something somewhere, if you just use this picture of a pitcher throwing 100 pitches, you can show a picture of where they usually are. And you could say there's a very high likelihood, 90% or more, that the next pitch will be somewhere within those circles based on the likelihood of where you think it would be. So this is the concept of a probability map. You don't know exactly where the electron is, but there's a 90% likelihood that it will be within that space. It is, again, pretty mind-numbing concepts, but this is the essence of what an orbital is, okay? So let's jump to that. So I'm gonna pause, let's see, maybe we'll move ahead for a second and see where we are. So orbitals. I've now defined for you what the orbital is. It is this region of space where you are most likely to find an electron. Within the Schrödinger wave equation, which is used to predict the shapes of these, they have found all sorts of weird and complicated things happening that we will be describing. So I'm going to pause at this point before I jump into the specifics of orbitals, but I will say this is where the end of the theory part ends. This is the part moving forward that you are going to need to be able to learn this part, because this is the bit we're going to start using as we start building on this. So I will explain to you the part you really need to know versus the part that's just the theory, but I will pause now and we'll talk that a second.